class. Okay, so let's get into a practice problem here. Got on the board here, we've got two charges, Q1 and Q2. Q1 is negative, Q2 is positive. And, if you have two charges, you can always draw a line through them, so we'll make that our x-axis. And they're separated by 3 meters. So we'll put Q1 at the origin, Q2 at x equals 3 meters. And we want to know the electric field at point P, where this point is 2 meters in the x direction, and it's the coordinates of P are 2, 2. From the origin, 2 in the x direction, 2 in the y. I'll write down the basic equation here. So the electric field due to a point charge is KEQ over R squared, where KE is this Coulomb's constant. And R is the distance from the charge to the point in question. So let's label these in the graph. Let's call this R1 and this R2. So R1 is the distance from Q1 to P, and R2 is the distance from Q2 to P. Now this isn't going to be entirely new, because the procedure is essentially the same as if we had a charge at that point P. We wanted to find the force on that charge. So first, but we just want the electric field at some empty point in space. Later we can put a charge there and see what happens. But let's start out by drawing the electric fields. So Q1 is a negative charge. So remember, to figure out the direction of the electric field at some point P, you start at that point P and you go towards negative charges and away from positive charges. So we'll call this E1. E1 points towards Q1. And Q2 is positive, so we go away. We move away from Q2. So E2 is that pointing in that direction. And we'll have to find angles and use sines and cosines to figure out the precise directions, but we can do that later. First step, actually, I'm going to make a table. Let's do that. We've got E1, E2, and the resulting electric field. So this would be the net electric field. And then we have our x and y directions. So right off the bat, if we look at E1, the x and y coordinates are both negative. Like if you're here, the arrow's pointing, down and to the left. Those are both the negative directions for our standard coordinate system. Where E2, we go in the negative x direction, positive y. So we want to start out by finding the magnitudes, and then we break them into components. And the reason I like to make this table in advance is you should really look at the picture in order to determine the components, because ultimately we're going to find angles and take inverse trig functions. And like I mentioned before, the inverse trig functions are a little tricky because we have, like, our electric field can point in any direction. Where if you take, for example, an inverse tangent function, your answer is going to be between minus 90 degrees and plus 90 degrees, being like quadrants 1 or 4. So, like, if E2, for example, if we took an inverse tangent, we'd probably get the wrong answer for that. But if we take care of the directions first, then we can always draw a triangle in a way where we're just looking at magnitudes to find the numbers to put here. And it's a little safer, I think, doing it this way. So let's find E1 and E2 to start with. need room. So I'll just write down the magnitudes here. So first we'll calculate that. So E1, that's our constant K. Now the charge is, okay, we've got a minus 3.7 microcoulombs. But very important, we just write down 3.7 microcoulombs. And I'm going to convert those just to coulombs by dividing by 10 to the 6. So yeah, micro is 10 to the minus 6. Just going to put it in the denominator to make it positive. And then we have to divide by the distance. So that distance would be R1. It's a distance from Q1 to that point P. So I'm just going to draw it here, and then probably will end up, try and make a little room here. Okay, so here's Q1, here's P, and that's R1. So again, we go 2 meters in the X, 2 meters in Y. So each of these sides is 2 meters. So R1, if we square these, we get 4 plus 4 is 8. So this is the square root of 8, which is around 2.8 meters. And this angle we can easily see is 45 degrees. We'll use that later. Now again, we can take the inverse tangent of 2 meters over 2 meters, which is just 1. Tangent of 45 is 1. Okay, so here we've got, actually R1 squared, that would be 8 meters squared. See, I took the square root. That was totally unnecessary, because what we really want is R squared. So again, we had, this is the square root of 8, which I rounded off, but 8 is exact. So it's better not to even bother with the square root. Actually, let me just erase that. Okay. Now it's just a matter of calculating this. Here we have 9 times 3 is 27 over 8. 10 to the 9 over 10 to the 6 is 10 to the third. Meters squared cancel out. One of the coulombs cancels out. So we have newtons over coulombs. This is going to be around, well, this is 3 3/8. So I think that's around 3.4 times 10 to the third newtons per coulomb. Okay, so I found the magnitude of E1. And again, remember, you do not plug that minus sign in there. We just want the magnitude of the electric field, so we put the magnitude of the charge in. Okay, now let's find E2. So I'm going to erase some of this. We have the same constant. Now our charge is 2.5. Oh, I misread that. This was, let me recalculate that, sorry. For some reason I missed that 0.7. So we have 3.7 times 9. So we had 33.3 and then divided by 8. So, yeah, that'll round off to 4.2. Sorry, I just misread that number. Okay. So now let's leave most of this on the board. But here we have 2.5 coulombs for the charge Q2. Now we want to find R2. So I'm going to draw another triangle. Like here's our point P. This is Q2. This is 1 meter, and this is 2 meters. So again, from Q2, you go left 1 meter and up 2 meters. This is at x equals 2. The charge is at x equals 3. So the difference along the x-axis is 1 meter. On the y-axis, it's still 2 meters. And so this is R2. I'll write this down. Here we had R1 squared is 8. Here R2 squared is 5. So we have 2 squared is 4 plus 1 squared, which is 1. So if we add that up, so this would be 5 meters squared. Okay. So let's clean this up a little bit. This coulomb cancels. We have newtons over coulombs. I'm going to do, here we've got 9 times 2.5 over 5. So that'd be 4.5 times 10 to the third newtons over coulombs. So again, 2.5 over 5 is 1/2. 1/2 of 9 is 4.5. And then 10 to the 9 over 10 to the 6 is 10 to the third. So E2 is 4.5 newtons per coulomb. Now, let's call this angle here theta 2. Now again, we want to use a trig function to find theta 2. And again, we have 3 options. Well, 3 with the standard trig functions. We don't consider things like secants or cosecants, whatever. But, you know, we take the inverse sine, cosine, or tangent. And again, it doesn't really matter which we use. But I would use tangent in this case. Say tangent of theta 2 is 2. So tangent is opposite over adjacent, so 2 meters over 1 meter, that's just 2. Now, why tangent instead of sine? Well, a couple of reasons. One, in order to take the inverse sine, we'd have to do 2 meters over R2, so we'd have to take the square root, which will involve some rounding off. But probably a better reason is these numbers are, you know, further removed, or this R2 is kind of further removed from the information we were given. Like, I'm very confident in these numbers. You know, go over 1, up 2. But then we had to calculate, you know, what if we screwed up calculating R2? Given these two sides, like if we got this part right, we could still screw up that calculation. So if we use R2 to calculate theta, then we get that wrong as well. So it's a little safer to stick with tangent. I don't know what the inverse tangent of 2 is, but let me just... Let's see. Inverse tangent of 2. $63 .43 degrees. Okay, and yeah, like said earlier, this is a positive number. This is just the magnitude of the angle. So we're treating these as just magnitudes. Now, you could try it this way where you say like tangent of theta 2. If you look at, you're finding like in this direction, we go like in the negative x direction. So you could have like minus 1 meter over 2 meters. Or sorry, 2 meters over minus 1 meter. And take the inverse tangent of negative 2, and that would give us an angle, you know, like negative 63.43. That would be like in quadrant 4, it'd be this negative angle. And so then again, that would imply that E2 is pointing, in the exact opposite direction that it's actually pointing. And that's because there's two angles that would give us this this ratio of 2/1. So just again, always be careful when dealing with inverse of trig functions. In this case, we're just dealing with magnitudes, so we're not going to run into any problems. We already know what direction the components of the electric field are going to be pointing. So now I'm going to leave this here. We don't need this anymore. I guess I could write it here. Hope it's... So theta 2 was 63.43 degrees. Hopefully that's readable. I don't read that anymore either. Now we have to fill in, we have to break these vectors into components. So let's look at E2, or E1. Yeah, let's start with E1. Okay, so E1, it's at a 45-degree angle. So the x and y components, in this case it doesn't matter because a 45-degree angle, sine of 45 and cosine of 45 are the same. So E1x is going to be, the way I drew it, this will be E1 cosine theta 1. So we have, I'll do that here, 4.2 times 10 to the third power newtons per coulomb times the cosine of 45 degrees, which is around 0.71. So let's see what that is. It's going to be around 3 times 10 to the third. So and these are in newtons per coulomb. Okay. Now, the y component is going to be E1 sine of theta 1, but that's going to be the exact same value. Because, sine of 45 degrees is also around 0.71. Okay. Now, let's look at E2. E2 is pointing in this direction, where we found this angle here was 63.43 degrees. I'll just write 63.4. And so we can say that E2x, we're just looking at the magnitude, this would be E2 times cosine of 63.4 degrees. So again, we want the x component that's adjacent to the angle, the y component that's vertical, that's opposite this angle. So here we have, I wrote this down wrong, it should be 4.5 times 10 to the third. Okay, so 4.5 times 10 to the third newtons per coulomb. And now we want cosine of this angle. 63.4. It's about 0.448. So let's. So I'm getting around 2 for the x component, around 2 times 10 to the third. Okay. And then for E2y, I didn't write this down for E1 because it was the same, but here, I'd have E2 times sine 63.4 degrees. So we need sine of this angle, 63.43. That's about 0.89. So if we multiply that, we get about 4.02, let's just say 4. And then, times 10 to the third. Okay, so what we've done now is we've found the components of E2. Well, both of them, E1 and E2. And then to find the electric field, you just add the components. So here we have minus 5 times 10 to the third. And here we have plus 1 times 10 to the third. Okay, so in a sense we're done. We wanted to find the electric field at this point, and that's exactly what we did. However, we have it in component form. It's often a good idea. Let's find it in polar form as well. So let's draw this. In the x direction, we've got, I'm just going to write down the magnitude. 5 times 10 to the third newtons per coulomb. Let's draw it as a vector. We're going to the left. And then we go up 1. Positive y direction. So the net electric field at that point P is going to be like that. Let's say it makes an angle theta. So we want to find the magnitude of the electric field and this angle to convert to polar form. I'm going to redraw this. Let's draw it a little bigger. So we go, this is EX, which is in magnitude 5 times 10 to the third newtons per coulomb. Then we go up 1 times 10 to the third newtons per coulomb. Okay, so to find the magnitude, I'm going to do this. So basically what I did is both of them have this common times 10 to the third newtons per coulomb. So I just kind of factored that out. So then when you add it up, you factor that out of each term, and we would have squared this factor in each of these terms, but then in the end we'll take the square root. So basically we have the square root of 26, just give me a little more than 5. Yeah, around 5.1 times 10 to the third power newtons per coulomb. So a little easier to factor out this common piece here, and instead of carrying through that calculation. Now finally, to find the angle, again, let's use tangent. So tangent of theta is 1 over 5, or 0.2. Again, that common factor cancels out. So tangent of theta is 0.2. Let's take the inverse tangent. It's around 11 degrees. Now again, that's this angle here. So one way we could write the electric field, if we want to write this in standard form, what we would do is we'd say 5.1 times 10 to the third newtons per coulomb. Then we could say at some angle, but in standard form, like say here's our, this is our x-axis. We measure counterclockwise from the positive x-axis. So again, going all the way around from the positive x-axis to the negative x-axis, that's 180 degrees, but we want to go, theta less than that. So the angle in standard degrees would be 168.7 degrees, if we want to write it in the standard form. So again, 168.7 plus 11.3, that would get us up to 180. Or if we had 0.3, that would be 169, plus 11 is 180. So this angle is 180 minus 11.3. So again, if you just see this, what's kind of nice about this standard form is if you just see this answer, then you can draw this vector and know exactly what direction it's pointing. Another way you could do it is you could have this and this and the picture. Because this, the picture makes it clear what direction this vector is pointing. So if I can see the picture and you say 11.3 degrees, I'm fine with that. If you just said 11.3 degrees and all I could see is like their magnitude and that angle, then I would think it was pointing in this direction. I think this was 11.3 degrees just because that's our convention. So again, as long as you're clear in some way, which, what direction the vector is pointing. I don't really care how you do it. Just know that it can be confusing if you just see the number. So again, this is just a standard convention, so you can always use that. But hopefully you would have drawn a picture in doing your work. So if you just took a picture of that and sent it, I would also accept that angle as well. Just the 11.3 degrees. Okay, and again, this is kind of the standard problem, like a two-dimensional problem, and we're never going to go more than 2 dimensions in this class. 2 dimensions make things easier because we can just have an angle to describe the direction of the vector, where if we had like a vector coming out of the board at some angle, we would need 2 angles to describe the direction of that vector, and the principle's the same, the math gets more complicated. And so 2 dimensions is kind of the right amount of complication for this class. Or, 1 dimension, it's a little easier, but you don't have trig to worry about. But yeah, we won't do any 3-dimensional problems. Now, one more thing I'll say, what if we had Q3 somewhere? Again, the procedure is exactly the same. Say Q3 was a positive charge, then we would have had E3, pointing in that direction. And we can make a triangle from Q3 to P and, find this angle. We can find that distance. So we could just make another row here for E3 and find those components. And then, the procedure is exactly the same. So as long as everything is in a plane, all our charges and the place where we want to evaluate the electric field, then we can find the electric field no matter how many charges we have, at least in theory. In practice, it could become very complicated. I mean, even with just 2 charges, there was quite a lot of work to do here. But, it kind of easily extends, this procedure easily extends to like any number of charges. Okay, so that'll be it for this. And again, if you can do these problems, then, you're in good shape when it comes to calculating electric fields for some given, charges. We're dealing with point charges here, and yeah. Okay, so that'll be it for this video.